Okay, well, next up in psychophysics would be the psychophysical equations themselves. So let's try to finish up these notes here. So as we've already talked about how to measure thresholds and the concept of a threshold, especially the difference threshold or just noticeable difference, let's look at what first Weber's results. And so what do we have here? So we mentioned, I think, a couple times previously that Weber was doing some research with lifted weights. So let's imagine a fairly standard procedure here. We're going to have a certain amount of weight placed in a person's hand. I'm just going to use my phone. I guess you probably can't see me too well. The light's just terrible in this room. I got my phone just sitting here in my hand, right? And so that's a weight, a mass that I would hold. And what we can do is we can come along and we can just place a little grain of sand on the phone. And you're going to ask your subject. So we would do this blindfolded so they can't see what we're doing. And we would say, okay, now, does this feel any heavier? And as you would imagine, adding a single grain of sand to an object that already has a pretty reasonable amount of mass on it, to it, would not be detectable, right? So you say, no, I don't feel any different, right? And there's no change in anything here. So what we want to do is we want to keep adding grains of sand. We could do something like a method of limits here, right? And we're going to keep adding more and more grains of sand until our subject says, oh, now I feel it. That feels suddenly heavier. That one last little grain of sand is kind of like the straw that broke the camel's back. And it says, oh, now that puts me over my threshold, what I would consider now the difference threshold, right? Now it feels heavier than it did before. All the other grains of sand don't really make a difference, but that one last one is finally enough weight. And so what we're going to do is we're going to measure, first we have the initial amount of weight that we started with, right? How much does the phone in my hand weigh to begin with? We're going to call that I for the initial stimulus intensity, right? And then after we have added grains of sand until the subject has reported that it is now perceptibly heavier, the extra weight that we have added is called the delta I, right? So delta is a mathematical operator that means change or difference, right? So the idea here is how much have we had to change I to create the just noticeable difference, and that's our delta I, right? And so what we call Weber's fraction is this right here, delta I over I is equal to a constant K. Now, what are the implications of this? This is relatively straightforward. Just give yourself a chance to think about the math here. If I'm starting with weight of a certain amount, and I want to add more weight to it in order to create a noticeable change, a noticeable difference, I have to increase the amount of weight, not by a fixed amount, but by a fixed proportion, right? So think about that. If I'm starting, I'd have to look back in the book or other sources to find out what the exact proportion was that Weber found. I think it was something like a 0.4% change or something like that, right? But let's just go with a 10% change because that's an easy number to work with, right? So if I had 10 grams of weight in my hand, then I would add 1 gram of weight, that would be 10% of that, right? To create a just noticeable difference. So if I started with 15 grams in my hand, if I add one gram to that, that's the same amount of weight that was sufficient to create a just noticeable difference when my starting weight is 10. But now if my starting weight is 15, what we will discover is that adding 1 gram is no longer enough to create the just noticeable difference. We're going to have to add 10% of 15 grams, which would be 1.5 grams, right? And likewise, we could predict that if we were going to put a 27 gram weight into someone's hand, then we would have to increase it by 2.7 grams in order to create a just noticeable difference, right? The idea here is that the amount of change, I'm just going to read off the slide right there. The amount of change required to create the J and D is a constant proportion between the final and the initial stimulus value there, right? And that's the idea here, is that the amount to create a J and D is not just a fixed number like 1 gram every time, but it depends on the proportional relationship between the extra weight and the starting weight, right? And that is Weber's, what we call Weber's law even, right? That this idea that there is this lawful relationship between the initial stimulus and the amount you have to change it is always equal to some constant proportional change. And K would be that 10% here, right? Now what we're going to do is we want to find some implications of Weber's fraction here. And what I have done is have simply just done a simple little algebraic rearrangement of the Weber's fraction formula. What do I mean by that? I'm going to multiply both sides by I, right? And so if I multiply both sides by I, then on the left-hand side, I will cancel out from the denominator there. And on the right-hand side, we will end up with K times I. And now we have a new formula, delta I equals K times I, right? It's just a simple little thing. Now, what I have also written here is another equation, y equals mx plus b. And you might remember this equation if you have taken, I don't even remember which classes you get this in high school, but hopefully you had this in high school, right? The idea is that would be the equation for a straight line, right? When you're making a graph, you have your x-axis and you have your y-axis, right? And if you have a straight line on that graph, it's going to have a slope. That's the rise over the run, right? How much does it go up relative to how much does it go to the right? And that is the m in your equation, right? B is the y-intercept, right? And that would be where the line crosses the y-axis. And the idea is that once you know the value of your slope and the value of the intercept, then for any value of x, you could plug it into this equation and solve for y. And then you could plot out a bunch of values and it would all fall on a straight line. And that would be a line with a slope of m and an intercept b. Now, I'm going to rewrite our new Weber's fraction, delta I equals K times I, but adding that plus 0 there, just so that you can really notice here that the form of our Weber's law is linear. If we have a y-intercept of 0, right, that is when x is 0, y is 0, that is if I have not changed if I have no stimulus, then a subject is not going to report anything, right? So we would expect that whether we're modeling an absolute threshold or a difference threshold, if I'm not going to do anything, the subject will not respond. So we would expect the y-intercept to be 0. And that's what, in that case, we don't really have to write it out, right? So we could just leave it at delta I equals K times I. So what this means is that what Weber's law or Weber's fraction is revealing to us is that if we could make a graph with the initial stimulus intensity I on the x-axis and the delta I, which is the amount needed to create a just noticeable difference on the y-axis, and there would be a straight line on that graph with a slope of k. And so what k is now showing us here is that that is the slope of the line that relates the initial stimulus intensity to the amount needed to create a just noticeable difference. Now, what we need to also think about here is that the amount needed to create the just noticeable difference is essentially related to a psychological response, right? Because that's what the just noticeable difference is. And so in a way, the x-axis is the physical stimulus and the y-axis is the psychological response in the form of the just noticeable difference. So we are now modeling a psychophysical relationship, right? We have the physical side of things and we have the psychological response, and that all turns into a straight line on our graph here. And that's what I am showing right here on the left. Assuming that k is constant for a given test, which of course that's the implication of Weber's law, is that we would have I on the x-axis delta height on the y-axis, and we would have a line with slope k and an intercept of 0. So you see that the line would cross the y-axis right down there at the 0 point. And what we would learn is that if we repeat these methods, but for other kinds of sensory modalities besides the weight in the hand, like maybe I wanted to do it for detecting the change in the loudness of a tone, or maybe I want to do it for detecting the change in the pitch of a tone, for the frequency of a tone. Maybe I want to do it for detecting the change in the sweetness of a sugar solution, or the sourness of an acidic solution. What I would find is that they should all be expected to conform to Weber's law and therefore have a constant slope, but they might all have a different K value, right? So what we might find is that the value of the slope differs across different senses. And what does that teach us? Does it teach us anything? Is that interesting at all? Well, it is, maybe slightly, because the slope of the line relates to the sensitivity of the system, right? So think about this. If I have a very, very steep slope, right? So think about what that looks like when you have a very steep slope. Here, on the left, our slope is kind of medium, right? It just kind of splits the difference between the x and y axis. But imagine it's steeper, which means it's pointing more up. What that would entail is that for a small change on the x-axis, the psychological response on the y-axis is just going up very dramatically, right? Small changes on the x-axis result in large changes on the y-axis. And that's, if you think about how the slope works, right? The rise, it's rise over run, right? So you're talking about a large rise for a smaller run on the x. So when you have small change on the physical intensity, but then large changes on the psychological axis, that's a very sensitive system, right? Small changes on the physical side become large responses on the psychological side. Conversely, a shallow slope would be one where you can make really large changes on the x-axis, and the line does not really rise very much, right? So it wouldn't change its response very much. This is kind of a neat finding, right? To discover this, imagine it's the early 1800s, nobody knows anything about sensory functions, and Weber kind of stumbles upon this idea that, oh, there seems to be this consistent relationship between these values. One of the things that Fechner, and again, if you read in the book, you're going to see more of this, that Fechner discovered is that, as it turns out, Weber was wrong, right? So if ignore the lines here on the right-hand side where it says reality, and just look at the little square scatter plot there, right? All those little squares of the scatter plot. What you might notice, and notice, I don't know if you can see my mouse pointer from the Zoom recording, but on the far left-hand side, the lowest values on the x-axis, whatever that lambda is, this is hertz or something for a tone, I guess. They start over 6, must be around 8 or 9 on the y-axis, and then they actually decrease when you get to 20 hertz on the x-axis, and then they start increasing again. But you notice, if you just kind of look at that overall plot as the x-axis increases beyond 20 hertz, that's really just a continuous curve, right? But what we might think about is that, what if we don't, when we do this experiment, whatever we're testing on the x-axis here, and we only choose values between 20 and 40 hertz, what we might find is that the results that we get, and that would be just those data points there, there's like, what, 5 or 6 data points there between 20 and 40 hertz. Those all approximately fit a straight line. So if I didn't run the complete range of stimulus values all the way from, say, 5 hertz all the way up to the 260 hertz at the end of the x-axis there, I might be left concluding that that really is a straight line function. And that's what that solid black line is trying to suggest here, is that Weber's law essentially works when you have a limited range of stimulus values that you have chosen in your experiment, right? And if you pick just one narrow little slice of this overall curve, you can approximate it reasonably well with a straight line. And then you might be thinking to yourself, I've done something good. But as it turns out, you have only got a narrow snapshot of reality here. And so when we do this experiment more properly and we use a much larger range of stimulus values, what we would see is that the entire thing is this ever flattening curve, right? And by flattening curve, I just means that the top of that curve is kind of leveling off a little bit. So what does this suggest? This suggests that at the lower levels of intensity, we have a slightly steeper slope so that the system is actually very sensitive to small changes on the x-axis. But as we keep increasing our intensity values way up to some higher levels, then the system doesn't respond very strongly anymore. If you remember when we were talking in the previous notes about adaptation effects, this is what an adaptation effect could look like, for an example, right? The idea is that when you're in the dark, your eyes are very sensitive to low levels of illumination. So very subtle changes in illumination are very easily detectable. But if you're in a bright room, your eyes are much less sensitive. So subtle changes in illumination will not be very responsive. You won't be very responsive to that, right? So this kind of curve could very much apply to sort of a visual sensitivity to light, as it turns out, right? And so Fechner, a few years later, was well aware of what Weber was doing and was trying to make sense out of it all. And as the story goes, he kind of had a mental breakdown and he spent like a decade lying in bed, just kind of worrying about all of this kind of stuff. And when it finally kind of dawned on him, his realization that what we should do is, I was already hinting at it, that we should treat the x-axis as a physical stimulus intensity, and we should treat the y-axis as just noticeable differences, which he considered to be a unit of sensation. And when Fechner realized this, that the y-axis should be thought of as units of sensations, that J and Ds are units of sensation, that's when he had the idea to create psychophysics, to actually create these kinds of plots that we're looking at here. Weber really didn't go that far here. So what do you want to, how do you want to make sense of this, right? Well, let's think about this for a second. Let's imagine we're going to do an experiment. Again, for simplicity, let's do a hearing experiment. And we're going to use the method of limits. And what we're going to do is we're going to start from 0. So I'm going to have absolute silence. And I'm going to ask our subject, can you hear something? And they should say no. And then I'm going to step my way up on an ascending trial into a point where they finally say, yes, I hear something. And so that jump from 0 to the first detectable stimulus, the absolute threshold, would be my first unit of sensation, right? And that's going to be on this graph here on the bottom of the slide. That's going to take us from SO to S1, right? And then what I'm going to do is I'm going to keep doing this. Well, now I want to detect a difference threshold above S1. So now that I've found S1, I'm going to keep increasing the intensity until the subject reports that it is now noticeably louder than before. And so I continue using the method of limits to increase the stimulus until the subject reports that now it is noticeably louder, and I have found a J and D relative to S1, and we're going to call that S2. And we can keep going. As you can see on that graph, we're going to go up to S1, S2, S3, all the way up to S8. Each one of those are sensation units, or J and Ds, as we have them labeled here. Now, Fechner is trying to make an argument here that these sensation units are all equally sized. They are all, that's why we're going to call them a unit of sensation, because they have common units. They are all the same scale. So they are linearly adding up. The spacing, if you look at the spacing of these dashed lines on this graph between S1, S2, S3, S4, they are all equally spaced out from each other, right? That's also what I'm trying to depict on this scale. So think of this as a scale or a ruler here on the center image here. And we have the Greek letter psi for psychological, because that's what these sensation units are. And we see that all of these hash marks on my psychological scale would be equally spaced as if they are units of sensation, right? I don't know if that's drawn perfectly, but just pretend that it is, right? Now, on the x-axis on our graph at the bottom here, we see the stimulus intensity. And what we know is that the stimulus intensity has to increase, right? So based on the curve that we had on the previous slide here, in order to create a just noticeable difference, it's not really a constant K, right? So rather what has to happen is that we have to change our delta I by not just a constant proportion, but by a changing proportion every time to map the physical intensity to a constant J and D, right? And so that's what we're seeing here, is that on the x-axis, even though we have the units labeled linearly there, 20, 40, 60, 80, 100, the actual values needed to create a just noticeable difference would be where those vertical dashed lines cross the x-axis, and you'll notice they are not equally spaced. We have to make increasingly larger jumps on the x-axis, because as that curve, and we can see this curve here that you can see on this graph, is just the same kind of ever increasingly flat curve that we saw on the previous slide. And what that means is that it's very sensitive down at low levels of intensity, so you can make small jumps on the x-axis and the curve ramps up very rapidly. But then past that inflection point, which is somewhere around 20 on this graph, it starts to flatten out. And that means we have to keep making increasingly larger and larger jumps on the x-axis to make anything meaningful happen on the y-axis. And that means even if we were going to try to keep going on the x-axis beyond the 100 here, then we would have to make really, really large jumps. And this graph if we wanted to continue this graph would just be really, really wide, right? It would just go on forever on the x-axis because we'd have to have really big numbers now, right? We'd probably have to go up to 400 to create the next J and D. And after that, we might have to go up to 2000 to create the next J and D. So we're increasing by essentially an order of magnitude. And an order of magnitude means essentially we've got a sort of an exponential function happening to the x-axis, but not to the y-axis, right? The y-axis is linear, but we have an exponential function happening on the x-axis. So how do we simplify that? Well, what we can do, and that's also what we're looking at here on the little scaling chart in the middle, where we got the physical axis with ever increasing distances. How do we make these two things match each other? That's what the logarithm does. So again, if you maybe remember some math to remember what logarithms do, is that they are essentially inverting an exponential function and returning everything back to a more simple linear scale. So that's exactly what Fechner realized, is that if the physical stimulus magnitudes are increasing in ever increasing units, whereas the psychological scale remains more fixed and linear, then we can use a logarithmic function to compress the x-axis and bring everything back to a simple linear function, right? So that's what we're looking at here. Again, we have the physical and psychological scales on top here, where we see the psychological scale is constant and equally spaced, whereas the physical scale shows ever increasing spacing. But once we take the log of the physical scale, now suddenly everything compresses on that scale so that all of the points line up. And so when we do a graph of R, this is what Fechner did, is he replaced with delta I, he called it R. But it's the same idea, it's a unit of sensation. And so when we do a graph of R and I on the bottom, we're going to get some kind of a curve, right? It could be like this one, or it could be the other flattened curve. But once we take the log of I, then we're going to end up with essentially recovering Weber's law, right? And so we're going to call this Fechner's law now, right? So we're going to, it looks a whole lot like Weber's law, except the fact that it has an R instead of a delta I, right? And that it has the logarithm inserted in there, right? You have to take the logarithm of I and then multiply it by K, and K would be the same K that tells us the slope of the function, right? But it's a log linear function here instead of a linear function. And so Fechner kind of invents psychophysics at this point, right? Really realizing this idea that we can kind of map physical values on the x-axis and these so-called units of sensation on the y-axis, and create these linear or log linear charts to visualize the transfer from the physical to the psychological. And then, of course, again, the same thing applies, that different values of K would correspond to different types of systems. Some sensory systems might be more or less sensitive than others. So that's going to be revealed still by variations in K. Now we're going to jump ahead a few more decades here, getting a little closer to modern times with psychophysics. And S.S. Stevens does this research where he decides to change the methods a little bit. So what he wants to do are studies that we nowadays call scaling methods, like magnitude estimation. And I think I might have hinted at a few of these kinds of studies in previous videos. So let's imagine a situation where I want you to estimate the loudness of a tone using numbers. So I just simply say, imagine the quietest tone you can imagine. We're going to call that a 0. Imagine the loudest sound that you can imagine, and we're going to call that a 100, right? So I just made up a scale, right? And it goes from 0 to 100, and 100 is supposed to represent the loudest possible sound you could imagine hearing before it just totally destroys your ears. And a 0 would represent the quietest possible sound, like your absolute threshold. And then I'm going to play a tone. And it's just going to be some medium level tone. And I want you to give it a number. And so maybe you should give it a 20, because it sounds like it's about 1/5 up from the quietest tone towards the maximum loudness, right? Or maybe it feels a little louder, so maybe you want to give it a 50 or 60. But the idea is that I've just invented a number scale, and I want to ask you to imagine where this particular stimulus would fit on your numerical scale, right? I could do it with the brightness of a light, right? So again, I'm going to say, imagine absolute total darkness. We're going to call that 0. Or I want you to imagine how bright it is to try to stare at the sun. Don't do that. And we're going to call that a 100. And then I'm going to ask you to look at some medium level light and assign a number somewhere inside of this scale. These kinds of experiments are all called magnitude estimation, right? And what that simply means is that I want a subject to estimate their subjective magnitude, that's a synonym for intensity, of the stimulus using some kind of a numerical scale like the one that I have just described, right? There's another variant that Stevens used called cross-modal matching. And so cross-modal matching would be something like, let's say now that I play the tone that has some level of intensity, and what I want you to do is I want you to adjust the brightness of a lamp using a dimmer switch so that these two things somehow match each other, that you judge the loudness of that sound to be somehow equivalent to the brightness of that light. Obviously, that's a strange ask of a participant, but you could kind of imagine that this might work. And that, of course, as you present different tones of varying loudnesses, they're going to move that dimmer switch for their lamp up and down to try to match that a little bit, right? And we're going to see, how do these systems map to each other? And maybe this can teach us something about our ability to discriminate and respond to different values of the stimulus scale, right? So again, we're going to kind of follow what Fechner did, and on our graph, we're going to keep the x-axis, the physical stimulus, but the y-axis is going to be the judgment that people made, right? Like in the magnitude estimation studies, it's going to be the number that they give. And one of the things that Stevens found is that when you do this kind of experiment for lots of different kinds of sensory systems and sensory judgments, you get a whole big wide bunch of curves like the ones shown here, right? Sometimes you might get a straight line. Sometimes you might get a curve like the one in the middle there, or the right, or the bottom. Some of these look a little bit like the curves we saw for Fechner, but not all of them, right? And so what this tells us is that maybe that log function is not really the best approach here, right? Because what we're looking at here is a psychophysical function that is that could be highly curved in lots of different ways. And the best way to model all of these different kinds of curves is to use an exponential function or a power law, right? And so now we have rewritten Fechner's law as a power law, R equals K times I to the power of N. And the N is the exponent here. So when it happens to be a straight line, we have I to the power of 1, right? But I squared, and if N is equal to 2, is going to give us that kind of a curve, or I cubed and so forth, or I to the power of 0.5, which is the square root, right, is going to give us that flattened curve on the bottom here, right? And so now we can see that Stevens' approach gives us quite a bit more modeling power, because what we're seeing here, and let's look at this, because this graph actually shows us some real results here. So I said before that your visual system's response to brightness levels might have that kind of flattened curve. And that's what we see here, is that when we use Stevens' power law to model someone's response to variations in the perceived brightness of a light, we get an exponent of 0.33, suggesting this kind of flattened curve effect here. Curiously, if we do a length perception experiment, what is that? So what I could do is I could show people various different kinds of objects that vary in their length, right? Like I could just hold up a pencil. I just got a pencil in my hand by coincidence, right? And I want you to tell me how long it is. And I'm going to use a magnitude estimation study and ask you to pick, maybe you don't pick a random scale like 0 to 100, and I just want you to judge it in terms of inches or centimeters or whatever units you're most familiar with. And so you look at it and say, well, it looks like maybe 10 centimeters, and maybe I choose another stimulus that's a little longer. So I want you to say maybe that's 18 centimeters or whatever, right? Turns out people are reasonably accurate at these kinds of tasks. And so we would end up with an exponent of 1, because as the object increases its length by 5 centimeters, people tend to judge it as being 5 centimeters longer, right? It would make sense then that changes on the x-axis are met by corresponding equivalent changes on the y-axis, and you would end up with a slope of 1. Not always, but sometimes we get pretty close to that. But let's look at this electric shock example, right? What we're looking at here is that accelerating curve with a very high exponent. And what happens, imagine we start at 0, right? So now our stimulus is going to be the voltage of the shock or something like that. So we go from zero, and person said, I don't feel anything, because obviously there's no shock. But we're going to bump it up to 10, and you're going to feel something, but it's going to feel like the lightest little tickle. So you're going to be like, meh, I don't feel anything. I mean, I feel it, but it's very mild, right? So then we're going to go from 10 to 20, and our subject would be expected to say, okay, I felt that. Again, it was pretty manageable response, just felt like a little tink on my finger, and that's it. Now we're going to go to 30. And that's when our subject might say, oh, wow, yeah, that was a pretty good shock. Doesn't hurt per se, but I could feel that fairly strongly. And then all of a sudden, look, when we go to 40, and imagine, try to extrapolate where 40 goes all the way up this curve. We've jumped up all the way somewhere around the 65 to 70 mark on the y-axis there, right? When the stimulus was at 30, it only goes to not even really to the 20 mark, right? And now suddenly we've jumped up to the 70, which means that our subject is probably going to suddenly change their answer to ow, right? Instead of just saying, oh, I felt that, now it's going to be a really sudden ow, that hurts. Imagine going to 50, the graph is already off the chart. That's probably going to be so painful that we're going to anger our subject if we continue to shock them beyond that point, right? So we see that that's a system that, is very insensitive to the very weak stimuli, but becomes increasingly more and more sensitive once we go beyond that inflection point in the curve, right? This teaches us some things about these different kinds of sensory systems, right? But it's not just about the K value that I said before, right? Because K is clearly not constant. It's about the shape of the curve. And the shape of the curve is modeled, just to come back here again, by that power law, by the exponent. Now, one thing we might also want to mention here is that whether or not Stevens is correct versus Fechner, I mean, Stevens gives us this ability to model these different kinds of curves. But what's also the case here that's worth mentioning is that Stevens also changed the methodology, right? By moving away from the method of limits and simply just presenting stimuli in various orders, or even the method of constant stimuli, where you're just asking people to report yes, no to the presence or absence of a stimulus, which is what Fechner was doing. Now Stevens is using these magnitude estimation studies, and he gets these results that better support the power law. And so there are still in psychophysics research some debates over whether Fechner's approach is superior because the methods are superior, or whether Stevens' approach is, right? So, but that's maybe beyond anything that we ought to concern ourselves with. Last up here, let's finish up our psychophysics with something else that we need to talk about. When we were talking about primarily using the original psychophysical methods, like the method of limits, and maybe also the method of constant stimuli as well, the fact that people sometimes make errors, and our approach to that is to average those errors out, so that way the mean threshold value that we measure is meant to be a measure of their true sensitivity to the stimulus. And one thing that we can do now is, with more modern statistical methods, we can maybe separately measure both of those factors, right? So we're not simply just going to average out the errors to measure the true sensitivity, but what we're going to do is we're going to use more complex statistical methods that will measure both the observer's sensitivity, that is recorded by the statistic referred to as D prime, and then we can also separately measure a particular person's response bias, that is, their tendency to say yes or to say no on a given trial is influenced by a particular bias to do so. And the idea is that maybe we want to do that, right? We want to capture all of these things that can influence an observer's bias in a psychophysical study. And that might be variations in adaptation or anticipation, habituation, all these things, right? Even sometimes it's just random. So we want to capture all of that randomness and variation, but we also maybe want to try to get at that pure measure of sensitivity, the D prime statistic. So this is using inferential statistics, and we have two distributions here, two bell curves that are overlapping each other partly, right? So what are we looking at here? Well, what we have, what are the things that this theory does is it treats the task as a signal detection task, hence the name, right? But it argues that signals are present in the context of noise. So in order to detect this signal, what it needs to do is it needs to be sufficiently strong relative to the noise. And so we're looking at something called the signal to noise ratio. In a previous video, I used an example of a person who has to listen for a monitor in a hospital setting that's beeping, but obviously there's a lot of background noise. So that makes it harder to detect when the monitor is going off, because maybe it's not loud enough relative to the background noise. So you would have a low signal to noise ratio. And if I need to make sure that this particular stimulus is definitely detected by whoever person's job it is to detect it, maybe I want to turn up the volume a little bit. So that way, yeah, I'm going to have an increased signal to noise ratio. By increasing the signal to noise ratio, this increases the likelihood that our subject will detect it. And that means that we have actually increased their sensitivity to that stimulus. And that's what these two curves are really trying to capture here. So the curve on the left is called the probability distribution of the noise alone situation. So what's happening when the stimulus is not present is you're going to have a variation in noise densities, right? And you're going to have all of these different kinds of situations where sometimes you might think there's something there and you're not too sure, but of course, there's never anything there when it's just noise. On the right-hand side is the distribution for the noise plus signal, right? So this is now a different distribution that contains the signal. And when these two distributions start to overlap each other, what that means is that the signal to noise ratio is very, very small, and it's very, very difficult to tell the difference between the signal distribution and the noise distribution, right? And that means there's going to be a lot of confusions and probably a lot of situations where you don't detect the stimulus. But if I increase the loudness of my stimulus or signal so that it is very, very obviously different from the background noise, the effect that that does have here is it starts to cause a horizontal separation in these two distributions. So that double-headed arrow called D prime, that kind of represents the distance between the peaks here. That is what's capturing the signal to noise ratio, right? So as we increase the volume, what we're going to do is we're going to take that right-hand bell curve and we're going to shift it further to the right to make it more and more different and therefore less confusable with the noise distribution. And once we separate those two curves and make them very distinct from each other, we are increasing D prime. But what that means is that we are actually increasing the observer's sensitivity to the signal rather than just to, and making it distinct from the noise. So let's imagine this, for example. There's various points, landmarks labeled under these things, right? So what is a hit? Well, when the signal is present and our subject says, hey, that monitor is beeping, that's a hit, right? That something is actually happening. And they said, yes, something is happening. So in a psychophysical experiment, if I present a stimulus and a subject says, yes, the stimulus is there, that would be considered a hit, right? Because they said yes, and it was really there. What we can also see, though, is that sometimes we might have a false alarm, right? So because these two distributions overlap each other, it's possible that sometimes when we have the noise distribution present, a subject might still say yes just to the noise distribution. So this means that there's no stimulus, but our subject thought there was a stimulus. And we saw some examples of that in the earlier psychophysical methods video, right? That sometimes people will say yes, even when there's maybe not a stimulus present, or at least something that's below their threshold. This is going to be called a false alarm, right? So it's like in a classic example of a false alarm, people yell there's fire when there's not a fire, right? That's a false alarm. So that's the same kind of situation here, is that now we can understand what false alarms are, is a place where the signal distribution and the noise distribution begin to overlap each other. We can also have what are called correct rejections. So that's when the noise distribution is present and our subject says, no, there's nothing happening. That's a correct thing to do, right? Basically saying, I reject the idea that there's something happening here, right? So it's a correct rejection. But of course, we also see the possibility that sometimes the signal is present and our subject says nothing's happening, and that's a miss, right? And that's a crucial error. So false alarms and misses would be errors. False alarm is saying yes when you should say no, and a miss is saying no when you should say yes. And then hits and correct rejections are correct responses, right? And so what we see is also this vertical line that splits the two curves here, called the neutral criterion. And what is called neutral because it's right in the middle there. But what we find is that separate from separating those two distributions by using on the x-axis by increasing the signal to noise ratio, which is going to increase our subject's actual sensitivity, we can also influence their tendency to say yes or no and that's captured here by the location of that criterion value. So if a person has some sort of bias to say yes more often, then what happens is that vertical line for the neutral criterion is going to drift to the right, because that's what the right-hand side of this axis actually represents, is a tendency to say yes versus no. And so if we shift the criterion further to the right, what we're going to do is the person's going to say yes more and more often. And that's going to increase their hit rate because they're saying yes, and maybe on many cases the trial is actually present. But they're also going to increase their false alarm rate because they're just saying yes to everything. And so if they say yes to everything, then every trial is going to be either a hit or a false alarm. You're not going to have any misses because they never say no. You're not going to have any correct rejections either because they never say no, right? And so that would be a very, kind of particularly biased criterion towards hits and false alarms. Now we could do the other thing. We can also try to drift our criterion towards the left of this x-axis, and that's going to increase the number of times our subject says no. And that means we're going to have lots of correct rejections, but also lots of misses and very, very few hits and false alarms. And so we can see here how two things are being measured at once, right? We can measure both the actual signal to noise ratio in subjects D prime, that's their actual sensitivity to the signal, but we can separately measure their response criterion. And that's going to tell us what their overall tendency is to say yes or no on a given trial. This little matrix helps us maybe better understand the decision chart involved in a signal detection task, right? So we have on the left here the actual observer's response. A yes is to say the signal is present. A no is to say that the signal is not present, so it's noise. So signal means yes, noise means no. And then what's the actual state of affairs in the world? That's shown on the bottom. Sometimes the signal is present, sometimes it's just noise. So when the signal is present and the subject says signal, that's a hit, also referred to here as a true positive. When the noise is present and the subject says noise, that's the correct rejection in the bottom right. That's a true negative. But as we saw, we can have false alarms. So the subject says signal, despite the fact that it's just noise. And we can have errors called misses. And that's when the subject says noise, but the signal is really present. And so what we can do here is we're not going to get into the details of statistically how the signal detection analysis works, but the concept behind this is what I was suggesting before, that we can separately measure the actual sensitivity to the stimulus as this statistic called D prime, and then we can also then measure the observer's tendency to bias their response towards saying yes more often or no more often, based off of a statistic that's referred to usually as beta in a signal detection analysis. Now, this has a couple of applications to the real world, and I want to mention that real quick before I sign off here. Imagine a situation where we're not doing a psychophysical experiment, but we're doing something like my hospital example, right? Where I have a person who is monitoring a patient and they need to detect an alarm monitor that's going off if this patient needs critical care intervention. So you would expect them to have a bias to saying yes more often, right? Because they're really worried that if they miss the signal, their patient might die, right? So we're going to try to minimize any misses, right? A miss is a catastrophic error. So that's going to bias our subject here, our medical professional here, towards more and more signal responses and fewer noise responses. Any tiny little beep that they think they heard, they're going to go check on the patient. So there's going to be lots of hits because whenever that thing is going off, they're going to detect it. There's also going to be lots of false alarm, right? Sorry about the dog here. Okay, I think he's done barking here. But what's going to happen, you might notice here, is that because we have lots of hits, that is, every time the alarm goes off, our person detects it, but there's going to be lots of false alarms, and these false alarms are going to result in this person running into the room every 5 seconds, every time they think the alarm's going off, and they're going to discover that maybe there's nothing going on of critical importance. And now they start to get a little tired, right? They start to think, oh, I'm tired of running in that room every single time I think that the alarm's going off. So they maybe even unconsciously start to shift their decision criterion away from that overly cautious bias towards saying signal. So now they're shifting more towards the bias towards the left, which is to say noise, to say no. And what's going to happen, of course, is that maybe they might end up, there's going to be lots more correct rejections and lots fewer false alarms, right? Less time wasted running into that room when there's nothing happening. But maybe now there's going to be misses, right? And these misses are going to be catastrophic, and then maybe the patient, dies or something that's terrible like that, right? So we can see the kind of real world kind of effects here, that in a real world situation when we have to pay attention to things, there's going to be a cost associated with too many false alarms, or a cost associated with too many misses. And whichever one of those costs is much more drastic to us is going to influence our tendency to say yes or no, or to say signal or noise in that given situation, right? So I just want to make that real world comparison there so that you kind of understand a little bit better what signal detection theory does. And now I think we have it all wrapped up.